Hello and welcome to the lecture on 7.5. Today we're going to talk about some more trig equations. Let's jump right in with an example here. Now, there are many trig equations that can be solved by using algebraic methods like we used in the last section, but some of them can't. For instance, this one, sine 2x minus cosine of x is equal to 0. How do you solve this one using algebraic methods? Well, you can't. We have mixed trig functions, sine and cosine, and we also have different angles, sine 2x and just cosine of x. So what we would do here is we need to use a trig identity to solve this one. So we use the double angle identity for sine. So recall sine 2x is equal to 2 times sine x cosine x, just like this. Since we have sine 2x, we can replace that with 2 sine x cosine x. We're left with 2 sine x cosine x minus cosine of x is equal to 0. Now we still have a sine here, but that's okay because we have a cosine in both terms. Now we can use the algebraic methods to solve this. We just factor a cosine out of cosine of x, and then 2 sine x minus 1 is equal to 0. We break this up using the zero product property. We have two things that are being multiplied together and their product is equal to 0, which means one of them has to be 0. We set them both equal to 0 in an effort to find where each of them are 0. So cosine of x is equal to 0 and 2 sine x minus 1 is equal to 0. Of course, cosine of x is equal to 0 when x is equal to pi over 2 or x is equal to 3 pi over 2. Now, we also have every period after each of these values. So we can add a full circle to pi over 2, and we would have a coterminal angle, which means that cosine of that angle would also be 0. So we have to include plus 2 pi k for both of these, where k is an element of the integers, and these solutions only solve the cosine of x is equal to 0. But they solve this equation as well because if cosine is equal to 0, then this product is 0. So these are solutions to the entire equations, but what I mean is we need to solve this one now. So sine of x is equal to 1/2, and we did a lot of these last section. So we will have x is equal to pi over 6, and x is equal to 5 pi over 6. Now again, we need to add full circles after that, any number of full circles. So we have pi over 6 plus 2 pi k, and 5 pi over 6 plus 2 pi k. And again, k is an element of the integers. And then you're done. So really, it's just one extra step for this type of problem. That is to use a trig identity to help facilitate the beginning of the problem and solving it algebraically. So after we use the trig identity, then we can solve it using the algebraic methods that we learned last section. Go ahead and try one. Cosine of 2x minus cosine squared x is equal to 0. Now don't forget, there are 3 different versions of cosine of 2x. If you pick the right one first, then your problem will go a little bit smoother, meaning you won't have to use another identity. Squaring both sides. Now, squaring both sides is kind of a tricky problem because, yes, it does give us solutions to an equation, but it also introduces extraneous solutions. So whenever we square both sides of an equation, we need to go back and we need to check all of our answers to make sure they actually solve the equation that we want them to solve. Let's say that we have sine of x minus cosine of x is equal to 1. Okay, well, there is no identity that I can use because we have sine of x and cosine of x. We don't have sine squared and cosine squared. And we don't have 2x's or anything like that. So there's no identity that we can use to help solve this. But what I can do is I can square both sides of this equation. So if I square both sides here, then I want you to keep in mind what we're trying to solve. We're trying to solve when sine of x minus cosine of x is equal to 1. Okay? And I'll come back to this at the end of the problem to show you the extraneous solution and why there is an extraneous solution. But when we square both sides, we end up with sine squared x minus 2 sine x cosine x plus cosine squared x is equal to 1, because 1 squared is still just 1. Now notice that sine squared plus cosine squared is equal to 1. That is an identity. It's the Pythagorean identity specifically. So we have 1 minus 2 sine x cosine x is equal to 1. So if we subtract 1 from both sides, we get the cancellation here, and we can divide by negative 2. And since we have a 0 on the right now, after canceling this 1, we would have 0 divided by negative 2, which is still just 0. So this will then become sine of x cosine of x is equal to 0. Now again, we have a zero product property. Sine of x times cosine of x is equal to 0, means that one of these two things has to be 0. So we come up here and we say, well, sine of x can be 0 and cosine of x can be 0. We just need to figure out for what x's this happens. Sine of x equals 0 when x is equal to 0 and x is equal to pi. Now, of course, we also have the plus 2 pi k for all solutions and not just the solutions between 0 and 2 pi. And then this one we solved already. X is equal to pi over 2, or x is equal to 3 pi over 2. And again, plus 2 pi k. And for all of these, we have that k is an integer. Now, we need to check our solutions, because if we don't check our solutions, we have extra solutions, and I'll explain why in a second, but right now I want to just check them. So if x is equal to 0, we go back to the original equation. Our original equation is sine of x minus cosine of x is equal to 1. This is the equation that we actually want to solve. So we plug in 0 for x, we get sine of 0, which is 0, minus cosine of 0, which is 1, is equal to 1. Well, that one doesn't actually work because we have a negative 1 on the left and a positive 1 on the right. So we can say that this one is extraneous because it doesn't actually solve the equation we want it to solve. What about pi? Well, we plug in pi, we have sine of pi, which is 0, minus cosine of pi, which is negative 1. So a negative 1 is equal to 1. This one works. Plug in pi over 2, sine of pi over 2 is 1, minus cosine of pi over 2, which is 0. So we have 1 minus 0 is equal to 1. This one works. Plug in 3 pi over 2, then we have a negative 1 minus 0. Negative 1 is not equal to 1. So we could say that this is an extraneous solution as well. I want you to notice something about these two extraneous solutions. Specifically, what happened on the left side in the step right before we squared. Now, we squared in the very first step. So if we plug in 0, notice that we get a negative 1 on the left and a 1 on the right. Now, if we square both of these, which is what we do in the first step, then we would have a positive 1 is equal to a positive 1. And that's because when we square both sides, remember, a negative times a negative is a positive. So when we square both sides, the negative goes away. But when we look at the original problem, the negative hasn't gone away yet. So that's why when we square both sides, we introduce these extraneous solutions, because they are negative versions of correct answers. If we had plugged in something and it came out to be positive 1, then it would have been a solution. But because it's negative, before we square, then it's not a solution. So whenever you square both sides of an equation, in order to solve it, you might introduce extraneous solutions. I'm not saying you will, because there are cases in which you will not introduce extraneous solutions, but those are very rare. Most of the time you introduce extraneous solutions. So whenever you square both sides, always, always, always check your answers. Another type of solution is a solution involving multiple angles. So I want to introduce this very slowly because this is a very tricky topic for a lot of students. Solving multiple angles. So suppose that we have the equation 2 cosine 3 theta is equal to 1. How do we solve this? Well, you might look at this and say, well, we have a cosine of 3 theta. We could try using the triple angle, which we haven't derived for cosine, but we could try doing a theta plus 2 theta and reducing it using the sum of angles and then reducing it again using the double angle identities. But you don't want to do that. When you have a single trig function with a multiple angle, there's a little bit of an easier way to solve this. So I want to do this in a couple of ways. First, I'm going to do it just outright, how we would normally solve it without doing a substitution, and then I'll do one with a substitution instead. So if we're given this, we can solve for the cosine like we normally do when we're just using the algebraic methods by just dividing by 2. So if we divide both sides by 2, we end up with cosine of 3 theta is equal to 1/2. Now what I want you to realize is that 3 times an angle is still an angle. It's just a bigger angle. So 3 theta is still just an angle. And whatever that angle is, it's going to make cosine equal to 1/2. So we think about, well, when is cosine equal to 1/2? Well, cosine is equal to 1/2 at pi over 3 and at negative pi over 3. So we say 3 theta has to be the angle that is equal to pi over 3. Because if we replace 3 theta with pi over 3, then this equation is true, right? Take pi over 3, replace our 3 theta, we have cosine of pi over 3, which is equal to 1/2. A similar reasoning, we have 3 theta is going to equal negative pi over 3. Now, of course, for all solutions, we would have to add the 2 pi k, where k is an integer. Now, so far, we've solved for 3 theta. And remember, it's just an angle. Don't freak out that there's a 3 in front of it. If we replace 3 theta with pi over 3, we get a solution. But in order to solve for theta, we just divide by 3. So this one will become theta is equal to pi divided by 9 plus 2 pi divided by 3 k. Dividing both sides by 3, we can divide each of these by 3. So pi divided by 3 divided by another 3 is pi divided by 9. And 2 pi divided by 3, of course, is just 2 pi divided by 3. And we do a similar thing for the second solution. Get theta is equal to negative pi divided by 9 plus 2 pi divided by 3 k. And these are our solutions now. Now, if you check them, remember that we're plugging in for theta, not for 3 theta. So pi over 9, if we plug that in for theta, we've offset this solution by a factor of 1/3 in order to account for this 3, is another way to think about it. So if we plug in pi over 9, we have 3 times pi over 9, and that will cancel, and you'll end up with just pi over 3 inside the parentheses, which will give us then cosine of pi over 3, which is equal to 1/2. Now with a substitution, I like to do this sometimes, but I feel like introducing it this way first helps a little bit. When you do a substitution, let's say that alpha equals 3 theta. Hey, remember, 3 theta is just an angle. And now it is the angle alpha. Alpha is just an angle as well. So we end up with cosine of alpha is equal to 1/2. We've solved this many times in the last section, where we have just a single angle here, and we have cosine of this angle is equal to 1/2. We look on the unit circle for what angles cosine gives us a 1/2, and we see that alpha is going to equal pi over 3 plus 2 pi k. And alpha will equal negative pi over 3 plus 2 pi k. We are looking for what values of theta make this true. Alpha has a relationship with theta, but it is not equal to theta. So we have to replace our alpha with 3 theta. So we end up with 3 theta is pi over 3 plus 2 pi k. And 3 theta is equal to negative pi over 3 plus 2 pi k. Click here, This was supposed to be a 3. And then we get theta is equal to pi over 9 by just dividing, plus 2 pi over 3k. Now don't forget to divide both parts by 3. Sometimes students forget to divide the 2 pi by 3. You have to divide both of them by 3. And here we get theta is equal to negative pi over 9 plus 2 pi over 3k. And of course, k is an element of the integers. Okay, so whenever we're solving for multiple angle, you want to set this equal to your solution for the cosine. Remember, we look for what angles cosine gives us 1/2, and then we set this entire angle to that solution. So in this case, it was pi over 3. So 3 theta, because it's the entire angle, has to equal pi over 3. I want you to try one. I'm going to do another one just like this in a second, but I want you to try one as well. Find all solutions to 2 sine 3 theta plus 1 equals 0. Find all solutions on the interval 0 to 2 pi. Now this is actually trickier than it sounds. It's not going to just be negative pi over 9 like we have here. I'll do one like this just to help you out a little bit. Example, solve 2 sine squared 4 theta minus sine 4 theta minus 1 is equal to 0. Okay, so this one I've put in a factoring part. Also, we have the multiple angle part. Now I'm going to do part A here, where we're just solving for all solutions, and then part B will be to find all of the solutions on the interval 0 to 2 pi. And I want to show you exactly how it works. So first, let's factor this. We look for two numbers that multiply to -2 and add to -1. Two numbers that multiply to -2 and add to -1 are going to be -2 and 1. So we get 2 sine squared 4 theta minus 2 sine 4 theta plus sine 4 theta 1 is equal to 0. But basically what I did here was I broke a -1 sine 4 theta into -2 and +1, which I got from here. So -2 plus 1 will equal -1 of this thing. Then I group it, factor out what I can. 2 sine 4 theta, sine 4 theta minus 1, plus there's nothing to factor out, so we just factor a 1 out. Sine 4 theta minus 1. And then notice that we have a sine 4 theta minus 1, sine 4 theta minus 1 in both terms. So I can factor this entire thing out. Think of it as a single object, and it's common in both terms. So I'm factoring this thing out, which is sine 4 theta minus 1. And then what's left here is 2 sine 4 theta plus 1 is equal to 0. Now we separate these into two separate equations. Sine 4 theta minus 1 is equal to 0, or sine 4 theta is equal to 1. Now, think to yourself, for what angle is sine equal to 1? You said pi over 2? You're right. So that means that this entire angle, 4 theta, needs to be equal to pi over 2. Think about it more like, if we replace 4 theta with pi over 2, then we get a solution to this equation, which means that 4 theta has to equal pi over 2 plus 2 pi k. Now there is no other place for which sine gives us a +1. This is it. Divide by 4 and we get theta is equal to pi divided by 8 plus 2 pi divided by 4. Okay, that's one of the equations that we get. The other equation is 2 sine 4 theta plus 1 is equal to 0. If we subtract 1 and divide by 2, we will end up with sine 4 theta is equal to -1/2. That's by saying 2 sine 4 theta plus 1 is equal to 0. Subtract this over and then divide by 2. Now we look for what angle sine gives us a -1/2. And in order to get the solution, we need to replace all of 4 theta with that angle. That means that 4 theta has to be equal to that angle. And the answer will be 4 theta is equal to 7 pi over 6, plus 2 pi k, of course. And 4 theta is equal to 11 pi over 6, plus 2 pi k. Now again, we're solving for theta, not 4 theta, so I need to divide both sides by 4 for each of these. And we get theta is equal to 7 pi divided by 24, plus 2 pi divided by 4, k. And here we have theta is equal to 11 pi over 24, plus 2 pi over 4, k. These are all of the solutions. Now part B is to find all solutions on the interval 0 to 2 pi. This is a little bit tricky, so be careful. Let's start with this one. Theta is equal to pi over 8 plus 2 pi over 4k. Now remember, k is an integer. Right? It can only be whole numbers, positive and negative. Now, if we let k be a negative number, say negative 1, because 2 pi over 4 is bigger than pi over 8, if we multiply this by a negative 1 even, then we would get a negative number, which is outside of this interval. So we're going to ignore that any negative k value. If k is equal to 1, then we have pi over 8 plus 2 pi divided by 4 times 1, of course, where k is equal to 1. If k is equal to 2, we have pi over 8 plus 2 pi over 4 times 2. K is equal to 3. We have pi over 8 plus 2 pi over 4 times 3. And if k is equal to 4, then we have pi over 8 plus 2 pi over 4, 4. Last one, left off on accident, is k is equal to 0, gives us just pi over 8, obviously. If k is equal to 0, it just drops this entire term. So we have pi over 8 plus 2 pi over 4 times 0, pi over 8 plus 2 pi over 4 times 1, pi over 8 plus 2 pi over 4 times 2, and so on. Now we can continue to do this infinitely many times, but I've already written more than enough here. Now, because we only want the values between 0 and 2 pi, so what we're looking for is when do these values stop being between 0 and 2 pi? Well, it will be listed in the angle, in the number of angles that you have. We have a 4 theta, so we actually only need 4k values, 0, 1, 2, and 3. I want you to see this. I wrote 4 out on purpose because I want you to see here. If we have k is equal to 4, then we can cancel this, and we would have pi over 8, which is a positive number, plus 2 pi. Think about that. Pi over 8, which is on this interval, plus 2 pi, which is the entire length of this interval. So it would put us outside of the interval, because pi over 8 plus 2 pi would put us over here, because it would be bigger than 2 pi. So these 4 are the solutions between 0 and 2 pi. Now you can also check them by just adding them up. 3 times 2 is 6. We'd have 6 pi over 4 plus pi over 8. If you actually add those together, you'll see that it's less than 2 pi. Let me do the other ones. You should pause the video and make sure that you can figure out the other ones by yourself, and then come back and just see if your answers match mine. So if we have theta is equal to 7 pi over 24 plus 2 pi over 4k, we have k is equal to 0, which would give us 7 pi over 24. K is equal to 1, be 7 pi over 24 plus 2 pi over 4 times 1. K is equal to 2, 7 pi over 24 plus 2 pi over 4 times 2. K is equal to 3. It would be 7 pi over 24 plus 2 pi over 4 times 3. Now, I don't need to write the last one, obviously, because this is not a solution. If we had 4, if we had k is equal to 4, again, it would cancel with the denominator, and we would have 7 pi over 4 plus 2 pi, which would put us outside of the range from 0 to 2 pi. And last one, theta is equal to 11 pi over 24 plus 2 pi over 4. If k is equal to 0, then we have just 11 pi over 24. K is equal to 1. We have 11 pi over 24 plus 2 pi over 4 times 1. K is equal to 2. 11 pi over 24 plus 2 pi over 4 times 2. And k is equal to 3. Gives us 11 pi over 24 plus 2 pi over times 3. And this will be all of your solutions between 0 and 2 pi. There are 12 solutions. K equals 0, 1, 2, and 3 for your first list. K is equal to 0, 1, 2, and 3 for your second list. And k is equal to 0, 1, 2, and 3 for your third list. So 12 in total. And they are all unique. These problems are tricky. That's why I wanted to walk through one. Last example, I'm going to do a really basic one, but using a different way. Instead of having a multiple angle, I'm going to have a fractional angle. So suppose that we wanted to solve tangent of theta over 4 plus root 3 is equal to 0. I know this one's pretty basic, but you should get the gist from here, from just this type of problem. Same exact idea as what we had before with the multiple angles. You solve it for the trig function, tangent theta over 4 is equal to negative root 3. So the solution will be theta over 4 is equal to 2 pi over 3 plus pi k. Remember, whenever it's tangent, you only need to do the pi k. You don't need to do 2 pi k because tangent's period is pi. You also don't need to look for another solution because there will only be one for each of these types of equations. Then we solve by just multiplying the 4 over. I want to show you something a little bit different. So if we multiply the 4 over, we end up with 8 pi over 3 plus 4 pi k. And this will be our solution. Now notice that there are no solutions on the intervals 0 to 2 pi. 8 pi over 3 is bigger than 2 pi already. And if we went to the negative version, that k is equal to negative 1, we're subtracting an entire 4 pi. That's massive compared to the interval length of 2 pi. So there are no solutions for this particular problem. Sometimes there are solutions when you have a fractional angle, but sometimes there are not. So when you have a problem like this where you need to find all solutions, and then you need to find the solutions between 0 and 2 pi, you're actually going to have very few solutions because of the nature of multiplying by 4. We're stretching the solutions away from 0, which means it might push it outside of the range from 0 to 2 pi. All right, that's going to be it for today. I will see you all in the next lecture when we start on chapter 8. If you enjoyed this video, please like and subscribe. All try one problems are on a worksheet linked in the description. The answer key and solutions are also linked in the description. If you want some free help, you can find me at twitch.tv/SkinnerPrincipal. Link is in the description, as well as my Discord server.